Alright, I want to make this video here where I go over some best fit linear regression. And first, so I wrote this Python program here, and I'll just go ahead and demonstrate it real quick for people with shorter attention spans. And so I can choose how many. So the basic idea then is we have this formula here from physics: final velocity equals initial velocity plus acceleration times time. The idea is we take some movement that we can measure multiple times, but for some reason, say we don't have the most accurate measurement of our velocity. So in this first example, maybe we shoot a cannonball out of a cannon, and we can take one, two, three, four, five different velocity, instantaneous velocity measurements at these different time values. And then we want to use linear regression to get a more accurate model of the likely true path of the object, and maybe even to predict future positions of the object. Or you can imagine the same thing, but a scenario with dropping a ball out of a window. And here I would have done 1, 2, 3, 4 measurements. And yeah, so that's the basic of what's going on. And then we use this to come up with a fill in the formula here so that we can predict future final velocity values at any given time value. So for starters, let's just say we took 30 measurements. And what this is going to do is generate a scatter plot with random velocity values, 30 random velocity values at 30 time values, and then do a best fit linear regression on that. So this is what it come up with. Here's the time values. The time values go in order, 0 to 29, and then we have these random velocity values that were generated. It produces this graph with the scatter plot and then the best fit overlaid on it there in blue. And it tells us the mean velocity, so the y column here is negative 31. The equation of the best fit line is final velocity equals negative 2.43 minus 2 times time. So this should be approximately 2 on the slope. It's a little hard to tell because the way to make the graph so that you could see all the plots nicely, it skews it. So you'll notice that the axes are skewed so that this goes 0 to 70 and then this goes 0 to 30. So, but this does have a slope of negative 2. And then it'll finish, when I close this, it'll finish the calculations. So we did some error calculations. The model has merit because the standard error of the estimate is less than the standard deviation. And the model indicates that 98.51% of the original uncertainty has been explained by the linear model. The standard deviation was 17.8. The standard error of the estimate is 2.2. And I'll just do it a couple times real quick here because it's kind of interesting to see how effective the random generator was on producing different graphs. So here you can see these look really close to that line, to be honest. It still has a negative slope. The slope is negative 7, which once again it's skewed, but if you look at the, what would you call that? Can't think of the right word. If you look at the spacing here, you can tell that this goes 0 to, this has 200 on the length there, and this only has 30. So it always looks like it has a slope of 1 graphically, but you can tell if you look at the, whatever the word is, the legend or whatever, that it actually has a very, very steep slope. And we got standard deviation was 62. That was really high, actually. Wow. It says 99% of the original uncertainty has been explained by the linear model. Somehow those don't seem quite like they add up, but we'll just go with it. So let's try a bigger number here, 50. Once again, you can see what's going on. Negative 6. It's funny, it keeps giving me negatives. It's random whether it's negative or positive, so let's just keep trying here. So we get a positive one. There's a positive one. And this time the slope was 4. the initial velocity value was almost 3. So there's the program running. Now, to explain the math and then to explain the program. So basically what we have then, I should have mentioned this already, but I'm using this, this was a book I used for my course on this. Where is my, you know what, my camera, see if I can move that during the video. There I am. So, yeah, this is the book that I used for my course that I did on this subject. And in case it was hard to read, there, applied numerical methods with MATLAB for engineers and scientists, except I'm using Python instead of MATLAB. We use MATLAB for the course. But yeah, so that's the book I'm going through, and they so here's the basic idea of what's going on. So if I pull this up, I didn't have it print off most of the columns, but here is the initial values. So the time, say what would be the measured time values and the measured velocity values, and time will be called x most of the time in the explanation, and velocity will be called y most of the time in the explanation. And you can see what we have then is this would be time 0, time 1, and so on, which just so happens here that time 0 is 0, but it wouldn't necessarily have to be that way. I just chose to do it that way. The example in the book did not do it that way. So yeah, so what we have then is we have this column of x values, which you can see here, and then we have the sum of the column of x values. Column of y values, the sum of the column of y values, a column of x values squared, and then the sum of that column, and then a column of the multiples of x times y at each point. So that would be 0 times 0, 1 times 10, 2 times 14, and so on. And then that would be represent like a column, and then you sum together all of the entries in that column to get this number down here. And then what we do then is we take those values that we calculated, we figure out the mean x, which is the mean time value, which is the sum of the x column divided by the number of entries, which here was 20. And we do the same for the mean velocity value. Then we calculate a1, which a1 is going to represent our slope of our line, and we can also call that the acceleration of our object. So a1 is going to be the number of entries times the sum of that multiple column minus the sum of the x's times the sum of the y's divided by the number of entries times the sum of the x values squared minus the sum of the x values individually and then squared after they're all summed. So that's how we get the slope, which again is the acceleration. Then to get the a0, which is the y-intercept or the initial velocity value, we take the average of the velocities minus the slope that we had just calculated for times the average for the x's. And now will give us the intercept value. So that's how we get the best fit linear regression, which is this equation right here in this example. It was velocity final equals 2.96, which is velocity initial, plus 4.14, which is the acceleration, times time. So this would not be on planet Earth, basically, unless we were calculating the horizontal motion, perhaps, of this cannonball movement. But actually, even still, it should be slowing down, not speeding up. But anyway, yeah. So let's see, anything else? And then the same is true in the errors. I won't sit there and go through every little detail here just because it's tedious and you can see it, and it's basically the same type of thing that I described above. Now to go through the program, what happens in the program. So in the first part here, we import some stuff that we need. I use NumPy because I chose to use NumPy arrays for part of it. Matplotlib is how we're doing the graphing. I started by clearing the plot. That way, if I run it multiple times, I don't end up with some kind of extra baggage from a previous run hanging out on the plot. We use math to take the square root, and I use OS to clear the operating system, to clear the console in between each run. Next chunk of code here, generate random velocity values that have a linear fit for each time value. And the way that I did this is it actually first generates the line. It doesn't use that line to graph, but it imagines a line, and then what it does is it it takes each point on the line and then produces an offset, either a positive or negative offset within a certain range. And I try to have it adjust the range based on the number of entries, because otherwise what happens is if you enter in a really large number, so let me just run this again with a really big number, you'll see that it basically looks like it just produces a straight line because my offset's not very good. So ideally I should have a much bigger, but it does adjust slightly for how big that number is. It just doesn't adjust enough. So yep, and let's get one of these in here in case I want to reference it that has numbers that make more sense. So let's try 10. So there we go. You can see the graph too. Okay, so yep, and that's basically in a nutshell of what's happening there. Then I have it graph the points. I have it adjust the window accordingly to the so the graph more or less fits in the window. I have it calculate the linear regression using the least squares method, which was the blue items here. And then once again, going through the columns there, because I'll just leave this one up. Summing the velocity values, summing the time values, summing the squares of all the time values, summing the multiples of all the times its paired velocity, calculating the average for time and velocity, time, velocity, calculate the slope, that's this right here, calculate the y-intercept, that was this right here, and then producing the output for the line. I have it slightly different based on whether it's positive or negative, so you don't end up with a double negative sign or a plus and then a negative sign in there. I could have left it, I just chose to not have it look that way. Then we graph the best fit line over the data points. So now that I've created this formula for the line, I now graph the formula for the line. So this formula that was generated from the best fit is what is actually being graphed, even though initially it is built more or less off of this graph just because that's kind of the way I had to do it to get it to randomly generate my scatter plot. It's not graphing from the initial graph, it's graphing from the best fit line off the scatter plot. Calculate error. So I don't need to run through this once again every single line. It's basically the same idea. You can more or less read my notes here and then read my notes over here. It's calculating the error and printing out the result at the end.